Maximilian Köhler, and he's a PhD student here in Bochum, and he will talk about mesh adaptivity. So, yes, please.
Yes, so my talk is entitled P4est data structures for Ferrite.jl, and in the keynote you already heard a little bit about what P4est is. And yeah, maybe another title for this presentation could be what to do if your actual work sucks. And then yeah, so maybe short history of frustration. So I'm in another project which is not related to adaptivity at all, but from time to time, also in my spare time, I started to work on this project because I thought it would be fun. And some parts of the library actually evolved yeah, from this code, which are used in different projects as, for example, the one in the discontinuous Galerkin efforts. And so you see here that I started with the first commit in 2021 in August, where I added lookup tables from the first, more or less, P4est paper. And then I started some work. And then here's basically a huge break or pause, more or less. Is there? Yes, but I'm a little bit confused. Okay, it went a little bit. Okay, no, I wanted to talk about. Okay, so here you see that I started to do work on neighborhood relationships. And before that, there was no way to query neighborhood information in Ferrite. And I thought it's actually useful in a lot of applications, not only now for this project, but also for one example is the topology optimization, where you want to compute a Laplace operator over a neighborhood of elements. So you need to know basically elements that are attached to a given element, and then you iterate over all the neighbor elements. And this should be a query that is just finished by a constant query. So there should not be a lot of work involved with that. It should be just give me the information and then you have the information, and not a lot of computation involved. And so I started quite immediately after having the first burst of motivation for this project to work on the neighborhood relation, because this is really crucial to have. And then this is the first break here, so more or less 1 year, where I then try to get the topology stuff merged into master. And back then I tried to have it working for all kind of corner cases that all Ferrite developers may have involved in their research code. So also with the mixed grid stuff, so that you have neighborhood information when your grids are mixed. And yeah, actually it was too slow. And this was due to the reason that I did not make any assumptions. So I did not make the assumption that there is no, let's say, 1D to 3D coupling in the mesh, because then you get quite fast into ambiguities. What is a neighborhood and what kind of neighborhood is this if you attach a 1D and a 3D element to it? And so Abdul and Dennis removed then like this no assumption approach with a little bit of assumption approach. And now the code for topology is quite fast, and it's also used in FerriteWiz. And yeah, I guess you can just use it now and live fine with it. And then there is another long break where I try to understand an algorithm of the second paper of P4est, and where I was stuck quite hard. And then Dennis helped me from time to time, and then we get it working. And I think now it's at a stage, so after 2 years, where you can do something with it. Okay, so first, what is P4est? So it's a library, of course, but it's also some sort of concept, I would say, or a gathering of concepts. And there, each octree, oh, sorry, I first need to explain what an octree is. So let's say you have a finite element mesh, which consists of quadrilaterals, and you may have one quadrilateral in the beginning, like this large one, and then you refine it once, and you end up with the 4 quadrilaterals here. So this is just one. And then you have this kind of tree structure, right? So you started with one quadrilateral, and you did an isotropic subdivision of it, and you have 4 quadrilaterals. And then you can, of course, subdivide one quadrilateral again, and then this node basically has again children. And so what you span up here is in 2D a quad tree, because one node always have 4 children, and in 3D you basically have an octree, because you always have 8 children with an isotropic refinement. And this is one tree. And a major concept in P4est is that each tree constitutes a coordinate system with a fixed size, and that is known a priori. So this is really important for this whole P4est kind of conceptual thinking. So let's say I allow here for a maximum refinement level of 2. So this is the deepest level, basically, this set that I allow. Then this octant has the size of 1. And this is why this trick is needed, because I need to know which octant at which level has size of 1. And then, of course, this octant at this level, at level 1, has the size of 2. And the root octant has a size of 4 in this maximum refinement level case. And this is really crucial that this maximum refinement level is set, because this introduces this fixed size coordinate system. Okay, then the implementation is actually quite, it doesn't need that much. And this is the nice part of P4est, I guess. And this is why it's capable to scale to quite a few cores. You only have for an octant 2 things that you need to store. And this is the level where the octant sits and the XYZ coordinate of the lower left coordinate. So this coordinate here. And then you have everything. This defines one octant, and it's uniquely defined in that way. And this is quite nice, because otherwise, if you may or maybe not have looked into other adaptive libraries, you see that a single adaptive cell can hold quite a few fields attached to it. So maybe the neighbor with whom is it sharing faces and stuff like that. And due to this, you get into problems if you scale your code to, let's say, a few thousand cores, because you have to do a lot of topological queries and processing due to this stuff that you save at this cell level. And here it's very the opposite extreme. You store as less as possible, and you try to recompute everything ad hoc whenever you need it. And other people would call it then a lazy approach, basically. And yeah, so this is the octant, and the octree itself consists more or less only of a vector of octants, and they store the leaves. So maybe let me switch back. So you only store in the left case this, and this. And those are stored in one array, a dense array, basically. Then you have the maximum refinement level, because this needs to be known a priori, otherwise your coordinate system is not defined for the octree. It's just an integer. So in the previous example, it was 2. And the nodes that are anyhow given for grids in Ferrite, which just define the physical node IDs. So those are the physical nodes, such that you know where your octree belongs in the physical space, where it sits, basically. Okay. So here I have an example. And for this, I need to explain you what the Morton index is, or Morton ID. And the Morton ID, you can think of it just as an integer. It's one integer. And the nice part of this integer is that it uniquely identifies an octant in one octree coordinate system. And you can go from the XYZ coordinate to the Morton ID in a bijective way. So you can go from XYZ to this uniquely defined integer, and you can also go back to it from this uniquely defined integer to the XYZ coordinate of the octant. And by this, you maybe can think of it that you just need now one integer to construct an octant, which is super cheap, because give me an integer, I can construct you an octant. And this is why this kind of lazy approach makes sense, because you can construct it super fast. And the construction is also can be done in a constant way, so algorithmically constant way. And the Morton index works in a way that is maybe not so intuitive. So if you number or you look at these numbers, they maybe make sense to you. So you go from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So they make sense. It's somewhat in X first, Y second, and then Z last convention. But this would be how they would be stored in the leaf vector that I just showed you in the octree struct. So this would be the index where you find those octants in this array. But it's not the Morton ID. The Morton ID works a little bit different. And you have to look at it on each level, basically. And here I'm querying the Morton ID on the lowest possible level. And then you see you have basically holes in there. And those holes exist due to the fact that you could split here once again into 1, 2, 3, 4, and then you would start with 5. And so this is why there is this subtle difference, so to say. Okay, in order to compute something, you need to do certain operations on the tree and also with other trees. But first, let's stick to just operations that are happening within the tree. So you have one octree, one quadrilateral cell, if it's not refined, so to say. And then you want to do some, let's say, topological querying on this tree. So maybe you have this case that you have here, once a refined cell, and I think it's, yes, a maximum refinement level of 1. And you have here the octant 1. So this is the Morton index in this case, and also the leaf index. So it's happened to be the same in this particular case. The XYZ coordinate, so the lower left coordinate, sits at 0, 0 of the octree coordinate system. And now you want to query neighborhood information only in the octree. So maybe I want to know who's the neighbor in this phase, who's the neighbor at this corner, or who's the neighbor at this phase. And by this, I would have basically the whole surrounding of the cell detected. And the neighboring of at this phase can be queried by phase_neighbor, and this is also how it's called in the P4est paper. So I tried to stick with the P4est paper conventions. So whenever you see an algorithm that I used from the paper, it's also named the same in the code base. And yeah, if you query now the neighbor at the phase index 2, you just get an octant which sits in XYZ with 1 and 0. And this operation is also super fast because all you do is basically bit shifting, but this is detail. So you can do this just fast. This is like the outcome of this slide. And now the important bit is that you can also leave the octree coordinate system. So what happens if I query the neighborhood at this phase? Then obviously I would leave the octree coordinate system, which has a fixed size. And this is, you can see this because what you would get is an octant that is outside of the octree at -1 and 0, which makes sense. So if you query here, then you get an octant here, and the XYZ is at -1 because it's the same size. Okay, and if this happens, you can always determine if an octant lies inside of your octree or not, because everything is fixed from the size. You know how big your possible octree system is, and if you leave the system, you can just compute this by checking if you are in the interval of the box that you are spanning initially. And if this happens, you need basically the topological information that are stored in the topology struct that you may know from the topology optimization example, or maybe also from the DG stuff that was presented today. And then you can query who is the octree neighbor, basically. And you can also do inter-octree operations. So when I have one octree here and another one here, and they have refined cells, how do those relate to each other? What is the octant coordinate and of octant here regarding the octree coordinate system of the neighborhood octree? So you can represent them in each other way. So this is a very, it's actually maybe a bad example, but you need to think of those now as different octrees. So previously they were just 4 octants, but now there are 4 octrees that are not refined. So they could all refine each other, and then those are separate trees that constitute a forest basically, right? Because there are multiple trees, and so it's a forest. So it's very important that you think of it now as separate trees and not of separate octants that relate to one octree. All right. So 4 octrees with a single leaf each and the maximum refinement level of B equals 1. So what could happen to this finite element grid basically is that all of them are refining here like this once again, and then you would have the maximum refinement reached in this forest at the top level. Okay, and now for showing you how the inter-octree operation works, I query to look at the octant, let me see. Yeah, so I want to know what is the XYZ coordinate of this octant here that lives in a different octant as this octant that sits here. So this is a coordinate system spanned from here until there, and here's a coordinate system that is spanned from here until there. And I want to know what is the coordinate of this one, this XYZ, from the perspective of this coordinate system. And I can query this with the inter-octree operations that are called transform, face, edge, and corner. And it's also the same as in the P4est paper. And if I do this with the octant 1 with respect to octant 2, I get -2 and 0 because they are not refined. They could refine once again, and this is why it's 2 and not 1 as in the previous case. Okay. So I need to hurry up a little. Now the problem is that you store as less information as possible. And due to this, it's quite hard to construct uniquely the nodes that are present in the grid. So it's trivial to construct all nodes in a duplicated way, but to collect them in a unique way so that you have not a double counting. So like just 1, 2, 3, 4, 5, 6 instead of 1, 2, 3, 4, 5, 6, 7, 8. This is the tricky part in this approach. And for this, I came up with a quite simple algorithm, I would say. You loop basically twice over the forest, and you distribute first all unique nodes based on octree index K and octant corner XYZ. And then you make another sweep through all of the forest, and then you remove your duplications based on vertex, edge, and face node neighborhood information. Okay, then another important part comes that you need to collect hanging nodes of the forest. And hanging nodes are, maybe I'll show it here in this example. A hanging node would basically be something like this or like this. So you have a node which is not shared with your neighboring element, and you need to constrain it. Otherwise, your solution will be discontinuous, even though you use continuous galactic methods. And so you need to collect them. I came up with some algorithm to it. You can see it in the code base as a function that is called hanging node, and it will return you all hanging nodes and their associated master nodes, so to say. All right, then another important piece for P4est is the 2-1 balancing, which means that you only allow a non-conformity level, or your hanging nodes have a certain structure to it. And this is that you do not allow such a scenario where you have a hanging node here, and the hanging node also depends once again on another deeper hanging node, because you would have a recursive constraint for this hanging node because it depends on this hanging node and also on those two nodes, and so it becomes cumbersome. And for this reason, the 2-to-1 balance is enforced. And how it looks, if you use the balancing approach that I've implemented, you come from the left figure to the right figure, and this is how it looks. You introduce new elements to it in order to get rid of it, but the downside is you have more elements. Yeah, I'm almost done. I also implemented, which is quite important, to reconstruct the boundary phase sets, because if you have Dirichlet boundary conditions and you introduce new octants and new cells, therefore, into your grid, then your Dirichlet boundary conditions need to adapt accordingly. So you introduce new faces that need to be constrained, or new nodes that are on the faces that are that need to be constrained. And yeah, and for this you need to reconstruct a boundary face set whenever you've done with your adaptation. Yeah. Now a very short story about the abstract grid interface. The abstract grid interface works in the sense that you can have a grid which is fulfilling the abstract grid interface. You can pass this to a DOF handler, which works as well. You can add a field to it, which works also quite good. But then you get an error if you want to distribute your DOFs. And this is not so much related to the abstract grid interface, but you would think that if you fulfill it, that you can just use whatever grid you have. But the problem is that you have this line of code when you want to distribute your DOFs. And here's the assumption that each cell, and cells are in our case here octants, need to know their nodes, their unique nodes, and they will never know this. So an octant will only know its XYZ coordinate and its maximum refinement level, and that's it. So we can never fulfill basically here this assumption. And this is why we need to have either special dispatches or a different DOF handler in some sense, or we need to change this assumption. So this is open to discussion, and this is why I'm presenting this. Yeah. So some open to-dos that I also want to tackle at the hackathon. In the beginning, you saw an elasticity example which is already somewhat functional. Problem is that in the L2 projection, there seems to be an issue with the hanging nodes and how to constrain them. And other than that, there is a lot of work regarding reconstructing topological information from the lazy approach. And yeah, I think that's more or less it, what I wanted to say.
Yeah, touch this. So are there any questions? Yeah.
Yes, so could you give an estimate of what this was going to do that I wanted to do it? Like how many steps are there left until I could
So this also depends on your error estimator. If we want to have a Sienkiewicz through error estimator, I'm not sure how familiar you are with it, but there you basically have a quite simple idea. So you have super convergent points. For quadrilateral, it's exactly the middle point of the element. And you can evaluate their stresses without having a stress field, right? And you have a solution, and from the solution you can construct a L2 projected stress field. And then you can compare the L2 projected stress field with the super convergent point where you know you approach the solution faster. And if it's off, then you refine, right? And this would be a not so fast approach with the L2 projection, but it would be the first step. And this is why I took this for the linear elasticity. And then the second step would be omit the L2 projection and go over element neighborhoods to reconstruct a fake L2 projected stress field, which is somewhat valid in this surrounding, which seems to be okay mathematical wise. I do not know why, but it seems to be okay. And then you do the same. And there are other classes of error estimator as like a Kelly estimator or something like that, where you need to go over the faces. And then you, of course, need to reconstruct the neighborhood information again. So the topology saves the neighborhood information, right? But it only stores it from the root mesh. So when you haven't refined it, and now you would need to reconstruct basically the face skeleton once again after refinement. I think it's not that hard. It needs to be done simply, but this is like one crucial step. But like adaptivity, solving with it, so we can always transfer it right now to a normal Ferrite grid. But I think it would be nicer if we can just iterate over this lazy data structure without materializing the full Ferrite.grid data structure. But yeah, I mean, it depends. I'm more or less begging for help. So there are a lot of open to-dos. I can show you where are spots, and then, yeah, but there's still some open work. I mean, you can solve FE problems with it. That's possible. But it's somewhat dependent on your error estimator, how long it will take. Oh.
The grid refinement itself, that's working and usable. The grid refine.
Yes, sure. So sorry,
Working and usable for.
I mean, this is fully functional. So here's a manufactured solution where I know the analytic solution. This is why the error estimator is somewhat perfect. And this is why you see the peak coming out. It's a singularity in the middle. And then this is linear elasticity after 8 refinement steps. But the error estimator is not working as it should, I think. And this is why it's not so nice adapted. But at least, I mean, you see that there are more elements here and a few there. So in principle, it works also with constraining, but only for linear ansatz. For quadratic or high order, we need to come up with a better way. It's not hard, but it's also just work that needs to be done.
Yeah, regarding the L2 projector, we should probably have a look at that again. It also doesn't handle mixed grids well.
Yes. Yeah. I'm just not sure actually mathematically also if it should work or if it shouldn't work. So we can discuss this also later because of the affine constraints, right? So we have here always affine constraints due to the hanging nodes. And I'm not sure if the L2 projector that assembles a mass matrix and has an already constrained or correct continuous right-hand side, if the left-hand side of the L2 projection problem should also be constrained once again. So this is more or less the question that is.
Okay, thank you. Okay, one more question.
Just simple one quick, because now you said that now it's not working with the typical node that you have, the special mesh type you have don't work, but this solution is then transferring it to a regular ferrite mesh and then solving or.
Exactly. So this elasticity example, and right, and also the left one, they solve a linear system. But for assembly, I have basically 2 grids currently because the DOF handler cannot distribute the DOFs on my data structure, even though I have the abstract grid interface fulfilled. But the octants will never be able to fulfill the cell interface, the abstract cell interface, because they know too less in order to fulfill what we expect that it should fulfill.
But you have to recompute it or reclose the DOF handler after each refinement. There is no quick path around that.
Exactly, it's a dirty hack. So to have the grid adapted, transfer it to Ferrite.grid, have a new DOF handler distribute to DOFs new, and then do stuff again. But of course, it would be nice to omit that.
But really nice.
It's also open work, where people with internal ideas from the DOF handler can do nice work.
Okay, so you can fix your computer.